Hey, welcome to the video. This video is about quantum entanglement, and today we're going to learn about what is it that makes us think that reality at the quantum scale is random and not something that we can determine. And something that I do want you to walk away from this video with is with a question. Question about, hey, why does this not make sense, and what is it that we're missing, and why is it that we have to just, go back to the randomness idea in order to explain things, and why can't we do this with our current understanding? And that's what we're going to do today. Okay, so we're going to approach this entanglement idea with a very specific form of entanglement first, which is quite interesting and easy to understand, which is a single state of half-spin particles. Now, first things first, what is a state and what is a spin? Well, let's start with the latter first. A spin. Short answer, we don't know what a spin is. Nobody really knows what a spin is. And then the long answer, we have to look at the story of how we got this spin first. So, the idea is that we had this experiment called the Stern-Gerlach experiment, in which we had these magnets, and you shoot off silver atoms in this, and you would expect, the atoms, they may just go straight, or they may deflect a bit, depending on whatever they do with the magnetic fields, how they interact. But interestingly, that doesn't happen. What happens is that you get two very distinct paths that atoms choose. They either shoot up or they shoot down. Nothing in between. And that makes us think that the atoms, they have an intrinsic spin to them, which creates this magnetic bar magnet sort of thing. And the magnets go up and they go down. And this is quantized, so that there's no continuum of, how much magnetic field can be there, and it's quantized. It's either spin up or spin down. It's either here, exactly here, or it's either here. That's it. That is spin, but it turns out that we know that physically it can't really be spinning there, and so we don't know what this property is, but we know its applications and implications. The applications are actually rather interesting. This is kind of the basis of quantum computers. This state is pretty much what is represented as a qubit, but well, later video. Right now, that is pretty much it. Spin. Now, the state is really the state of the spin, right? So is it spin up or is it spin down? That's the state. So spin up, that's spin up. Spin down, that's how we represent spin down. And that's pretty much the basics. We're going to see how entanglement entangles the state of two particles that are entangled. So let's understand this. And just to be clear, we're first going to discuss what we measure and what we kind of experimentally determine about the properties, and then we're going to kind of discuss what models fit those measurements and everything that we observe. What models can explain what aspects of those. So here's what we've come to know about the spin of particles and entangled couples that are singlet. So rule number one of the game. Rule number one is quite simple, as the name suggests, and as you might know about entanglement, always measure in the opposite spin, right? That's the rule for entangled pairs. Their spins are always measured as opposites. But there's a catch to this. This is always true for a few cases. Okay, this is always true when the axis is the same. In other words, you could have this turn and go like experiment. You could have a measurement apparatus here, have one here. In this case, these two entangled pairs, this one will measure up, and so this one will measure down. Certainly, 100% of the time. However, you could have, say, something like you can twist the apparatus here. Another thing that you may know is that it is always true, irrespective of distance across space. Okay, so let's say you measure this particle over here, and you measure this particle, say 1 kilometer away over here. They will still be in the opposite spin states. That is the second point. And let's add a little time here. In other words, if you measure it, say, today, and you measure this tomorrow, again, this will be in the opposite states. So, well established, it's always opposite as long as the axis is the same, and, well, the distance and time don't matter. This is the key factor. Okay, rule number 2, major rule number 2. This is another thing that we observe. We observe that if measured once, a following measurement, pardon me for my handwriting, will be the same cos of theta by 2 squared times for theta being angle between axes. Now, what on earth is this statement? I know, well, this is, not the best in framing this, but here's what this means. Say you have a particle here, and we don't know its state right now, so now we push a question mark here, and we measure this here, and we get a spin up. The next time that we're going to do the measurement, say you do the measurement here. Now in this case, the measurement can be here or it can be there. Okay, the probability of it being, let's say that is the face of the apparatus, north south, that being the same state, it's corresponding to the north side, which means that it's spin up, is going to be there this percent of the time, or this fraction of the time, which means that if the angle between the axes is 60 degrees, then let's do cosine of 30 squared is going to be root 3 by 2, so 3 by 4. So 3 by 4 times we're going to get a spin up, and of course the conjugate, or 1/4 of the time, we're going to get a spin down. And that is what the statement means. This is what we've observed, right? Particle measured, the following measurement will just be the same, cosine of the theta by 2 squared of the time. That's the rule of the game, and now we're going to discuss a few implications. Okay, now let's grab one more piece of paper. Okay. So what model do we attach to this to explain all these results? Well, firstly, let's think about the entanglement generator, right? So let's say that this is the entanglement generator. Let's call this a black box. Okay, this generates two particles. This one particle, that is another. Right. So the first idea that comes to mind is that, of course, well, you can have a particle, say let's say this generates a spin up and a spin down particle, right? So the first idea that comes to mind is that it generates a definite state. But then you know, each time you generate the particle, when you measure it, the measurement is not always spin up. How do you explain that? Well, maybe you generate a definite state out of the black box, and you know, maybe it's thereafter changing. So maybe this one is, you know, spinning this way and this one is spinning that way, and they're spinning the opposite ways. So whenever we take a snapshot of time, you know, they're in the opposite states, and that's totally valid. You know, that's kind of doable. Except that doesn't work because of this property that we observe. See, if we take this thing and we take its snapshot in time once it's in the up state again after a rotation, and we let this rotate a little time further and we take its snapshot at that time, then you see both of them being in the same state. But we never see that as long as the axis is the same. You know, it's irrespective of the time. So we know that the state cannot change. You know, the state cannot change. So it has to be a definite state, and it has to maintain that state. Okay. So maybe because we observe a random state each time we measure things, maybe the thing generated by the generator is not definite, and it is kind of random. You know, there's some intrinsic randomness or errors in our generator, and that's totally fine. You know, this is a totally, you know, physically determinable system, and I can just flip the coin, and you know, as long as I don't measure it, I don't know which way the coin is facing up or down, but it's there. Well, it's already determined, and well, there we go. So the same idea is there. You know, the generator, it has some intrinsic variables that we don't know yet, and we just generate the two particle pairs that way, and they just fly past in the state that they're in. It's totally determinable. And let's see how that plays with our roles. Okay, so as long as the axis is the same, they are the opposite states. All right, so it works for this one. Irrespective of the distance across space and time. So if you measure this, here, well, this is state up, and if you measure it further down there, still state down. That checks out. And you know, regardless of when we do this in time, this, because they maintain their state, this seems kind of promising, right? I mean, this observation has been checked out by this model. So let's now consider a very sneaky thing. Let's take this measurement for different axes. Let's measure this particle about this axis, and let us measure this one about the same axis, which again is 60 degrees, right? And you know, now you would look at this and you're like, oh, so this we know that this is state up, and we know this is state down. I mean, we don't know it, but the particles themselves know it, and so we would expect the particles to be spin up here 3/4 of the times. So 3/4 of the times we're spin up, and 1/4 of the time we're spin down. And over here again, 3/4 of the times we're spin down, 1/4 of the time we're spin up. And you're like, all right, that doesn't seem that bad, except it is. And the reason it is bad is because now you can have a situation where probabilistically, you know, you can have a spin up and a spin up, okay? And to be precise, you know, there's 3/4 chance to spin up and 1/4 chance to spin up. So 3 out of 16 times, they're both going to be spin up. But we know that irrespective of the axis, as long as the axis is same, so if this or that, it has to be the opposite, so this doesn't work, and so this model altogether, it just doesn't work, because of this, because of the time thing. You cannot have a definite state which then changes, and because of these two properties combined, we know that you cannot have a random state that is maintained. So this definite state thingy, or particle itself having a certain state, which we then measure with the Stirling-Gerlach apparatus, it's just wrong. It just doesn't work. But the randomness doesn't come in quite yet. There's another way to kind of look at things, and that is that the particles, they converse, they chat. They're kind of clever. They're really clever. And this one says, hey, if it's like that, I'm gonna be stayed up. And as a result, this one has to say that I'm gonna be stayed down. And they decide that they're gonna do this for this, that, and that. They're gonna decide their own states. So this one says I'm gonna be stayed up, and I'm gonna be stayed down for this one. And so this one says, because I have to be the opposite by this rule, I have to be down and up. Okay, and they do this for all the different things. And well, let's see. All right, we're back. So the particles are clever, and they determine these plans, right? So they say, aha, if it's like that, or like that, I'm gonna do this. And this says, all right, I'll do the opposite. And they make this plan, and they're like, aha, all right. If the axes are the same or the opposite, it's irrespective of the distance in space or time. And well, if one is measured, the entanglement is broken, and then we can do whatever we want. And so that works. Except there's one more catch here. Let's say I choose to measure particle 1 with this axis and particle 2 with a different axis, right? This axis. Now we look at, this is going to be spin up, spin down, spin up, spin down, spin up, spin up, spin up, spin up. Oh, now they're different, and they're different by exactly a half. They're different by exactly a half. And it turns out that if you do this experiment and you choose two different axes on an entangled pair of particles, you actually get the same probability here. They're different 3/4 of the time. Different 3/4 of the time, and that somehow doesn't work here. And you may say that, oh, maybe they don't choose to decide this one, right? Even then, if you tally these up, they're different only 1/3 of the time. And so no matter what you do with this definition, because this is independent of the laws of physics, and this is the only probabilistic states that work, it's the only matrix they can make up of this, this is never approached, it's never reached. And so it just turns out that this clever kind of hidden variable communication thing before measurement doesn't work. The only way it turns out that you can explain this is if they're completely random. They're completely random. It's the third way to explain this. And you measure that, spin up. The only way to explain it, as of now, is if instantaneously this part is now spin down, as if the state of the other particle is only determined after measurement and not before measurement by any means. So you cannot have the particles have a definite state or a random state, or converse their possible states before the measurement. The only way you can act on the other particle is if you act after the measurement, and that is the spooky action at a distance that, you know, Einstein thought is kind of weird. So the only way that you can, you know, kind of explain how things work is if the information exchange is upon measurement and not before the measurement. You know, you cannot have any state either random or definite, or you cannot even have, you know, information conversed before the measurement, because all these, they do not satisfy all these properties that we have. The only thing that satisfies it is if the information of the state is kind of, you know, conversed from this particle to the other, and by some means, some spooky means, upon measurement. And that kind of is what is mind-boggling for all the scientists out there. And that really is not that, you know, intuitive. And yeah, that's probably the only thing that works. And so I want you to go home, or if you're watching at home, I want you to think, oh, how do I explain these properties by not using this spooky action? And you will kind of realize that, you know, these are the only possible things. As long as you know, link these, and even this to some extent, I'm not satisfied with this. I mean, particles will not converge, and, you know, all that. But it's kind of interesting to see how, you know, it is going to be random. It is not predetermined, and upon measurement, this randomness code is broken in a way that they're still correlated. It's really insane. Good luck. Take care. Stay curious, and may the kid remain.